Any other questions on this, or?
Just gonna take time to go through things.
Yeah.
You have an email from me for pending approval of my.
Okay. Yeah, no shortcut to it is just a lot of content because we're trying to do an integrated design process that just has a lot of elements. But let's talk about a couple of practical things. So one, safety. So that torch stuff. So let's talk about cylinders, gas cylinders. They're high pressure. They're 2,000 psi, which means that if it falls over and the top gets knocked off, it becomes a torpedo. I mean, literally, like if that happened, like in the middle of a stadium, the thing would fly over the stadium and stuff like that. It can be very, very. It's very energetic. The amount of pressure and force that's stored up when you have this gas that's at 2,000 psi, it's 100 times that of more than 100, like 150 atmospheres, but it's really, really powerful. So the thing is about the tanks, they're on carts, but they're chained up together, so they can't fall apart. Or if they fall, like the whole thing has to fall, makes it much harder to knock off the actual fittings that are on it. But if you knock off the top, like you're gonna get a massive. If you actually knock off the fitting that's at the top, like the knob, you can have a very dangerous situation. The thing will like just destroy the whole workshop, just fly through it like a torpedo. I mean, it's serious. It's serious stuff. So, like I noticed, you exchange the tank. You got to put it on a cart and put the chain around it. So the likelihood of it just tipping over and breaking off a fitting. I mean, if it just drops over, lands in a bad way and hits something, it could knock that fitting like right off. It's like.
Can we put them inside of a structure to prevent that? Rebar structure or anything?
Well, I mean, it's like literally think of a torpedo. I mean, but there's ones that we move around. You have to move them around because the torch is portable. So the standard practice is if you move in the tank, you got to screw on the top. If it lands, the way the top is designed, that cover cap, not the knob that you actually turn it on, but the cover cap, this little cylinder thing that goes on the shroud over the top. If you fall over, that thing doesn't come off. It's quite safe. But if we're moving a single bottle, you gotta keep that on. Don't move a cylinder, a full cylinder that's got the top, the knob actually exposed, because it's like a 3/4 inch fitting or whatever. It's pretty thin up there. You can knock it off and cause a very dangerous situation. On the carts, but you got that new one out there that's not sitting on a cart. So if someone knocks it over right now,
No, that's empty too. I moved that from the other torch that was all empty.
but the one, so how are you cutting if they're both empty?
I'm not. I reamed them out with the drill instead.
Oh.
This works.
Oh, so you picked up one that was empty?
Yeah, I was just checking. I was like, I don't know if
Oh.
the gauge is working on this or if it's actually empty.
Okay.
I just took it over to the torch.
Yeah. We should have like, I think there's another full, the ones that are full are in west, back, not by the entrance, but more like in the corner. But yeah, that's just a safety thing. Standard is the chain around it, bonding the two bottles together, so it's much harder for them to fall off. And in the cart, it's a little more stable. But also on the welders, there's a chain around the welder bottle, gas bottle. Make sure that's on, and not like, don't hang the chain where it's like got a bunch of slop, because it could still possibly fall over. Get it tight so that the chain is hugging right against the bottle, so if you like tip, it's just much harder for it to fall over. Yeah, that's one thing. Let's talk about the very important topic, just practice in the workshop. You put in just notes in the critical path doc. How do you cut steel, and what tools are usable for cutting steel? Because there's like so many different ways to cut things, whether it's wood, steel, or other materials. But let's do a survey of that real quick, just to appreciate some of the subtleties there, because there's just so many ways to do it. So this is like, I started thinking, okay, so I started, okay, how do you drill a hole or cut a thing, and then it turned out into this 40 item list. So because there's really a lot of ways you can do it. So
Wait, did you just remove? Oh,
no, we gotta enlarge that thing. Okay, tool use. Cutting steel and holes. So first you have to consider what kind of material you're cutting in terms of profile, whether it's solid or hollow. So solid, hollow, thick, thin, irregular, because you're going to do different tooling for whatever geometry you have. And you have to understand that from the get-go. The tools available are ironworker hole puncher. So first with the ironworker, where to use the ironworker. And here you can do like a whole, like a two-dimensional chart showing like material thickness or like shape versus like what's the ideal tool to use. And you get clusters of, and you'll see like, but you have to have this whole picture of, okay, if I want to do something like a cut of some sort, which is the first thing I turn to? And what's the capacity, including safety, speed, cleanness, precision, and all that? Okay, so what's an ironworker good for? What kind of, so talking about solid, hollow, thick, thin, irregular, what can we do with the ironworker? What's it good for? Like say you got some steel to cut, is your first choice the ironworker?
Flat.
Flats and thick. What about flat and thin? Like 1/4 inch.
Depending on the precision, maybe.
How precise is it? Is the ironworker?
It looks pretty
It's pretty precise. It's pretty right on. Because the blade gap is only like 7/1000ths or so. So you get a pretty clean cut. So say you want to cut. We're cutting the plates for the torch table. They're 1/4 inch. What would be our first choice? We use the ironworker. So we got 12 inch wide stock. How would we cut it?
Not with the ironworker because of the shape and complexity.
For flat for the carriage metal piece?
For the blades, that's what we're talking about, right? I said that-
Oh no, not for the blades, but
I thought
for the
this-
torch
that's-
table, the actual carriages of the universal axis, just the flat pieces.
Oh, I thought you said for the blades for the.
Oh, sorry.
Yeah, so yeah, for,
Ironworker. What would be your next tool? Like say the ironworker was out, the power cube ran out of gas. Where do you go?
Add another power cube.
You could do another power cube. In which case would you do it versus, okay, I gotta drive live track back in. At what point would you say, I'm gonna get the other power cube versus, nah, I'm just gonna do this other thing? What's your next best choice?
Angle grinder. Angle grinder.
For
Is that
1/4
it?
inch? No, not angle grinder. Angle grinder at most you'd ever do is like 1/8, but not for long linear cuts. You can do the cutting blade on an angle grinder, that's the thin one, but it's slow and you can't. The danger is if you torque it, like you can get the blade stuck. If you don't go vertically down, you torque that, it'll just rip and possibly injure you. The blade will shatter. For safety wise, I don't like using the cutoff wheel on angle grinders, because if you're doing a thin precision hole and you torque it, you're going to catch your blade. I see a lot of people gravitating towards the cutoff wheel. Like I'd like to see that thing like almost never used. Safety reasons. If you're going to do a cut of something, just take it right on an abrasive cutoff. The 14-inch abrasive cutoff wheel. That's safe because you can clamp the object. For the abrasive cutoff, you have to hold that thing. That thing can move if you catch the blade. That's the real danger of it. Try not to use the cutoff. I never use it because of that. I mean, unless you're paying attention the whole time, it's a dangerous tool. So, hole puncher, thick metal, up to 1 inch. We sheared the 1 inch for what? Oh yeah, for the counterweights, and it could hardly cut 1/12. I had to just keep going back and forth to cut it. But yes, for 1/4 inch, yes, definitely not grinder for 1/4 inch. Angles too. Ironworker does angles. Quick way to do angles. Okay. Hacksaw. What's the limit of a hacksaw?
Elbow grease. Yeah.
Yeah. Well, okay. Let's kill off. So, I think we never got to. Will we take out live track or use the torch? At which point The torch, I mean, that could be pretty quick. Say you had to cut that out of, like, say 12-inch stock, you have to cut 12 inches across. It's pretty fast, but what's the disadvantage of that? You got all this cleanup at the end. It's as straight as you can run with your hand against the guide. But you can definitely do that. You can definitely do it. It's fast. Grinder, no. Circular blades, there are metal cutting circular blades. There's a thing called a cold saw, which is like the abrasive cutoff saw, but it's a slow moving metal blade and it's water cooled, like liquid cooled. We actually have one, but we hardly ever use it. It's not really set up. Okay, hacksaw. Can you cut, like, would you ever cut a 1-inch rod with a hacksaw?
1 inch.
Yeah.
Could, yeah.
How long would it take?
Depends on the fact that
Could,
If you like really get into it with a hacksaw, maybe like 5 minutes of non-stop, but it's very tiring.
I think I could do it in 4.
All right. So how would you? So how would you cut a 1-inch shaft?
use the, what do you call it, the abrasive cutoff saw?
Abrasive cutoff, that's the best. What about 2-inch shaft? Would you take that on abrasive cutoff?
which one would be abrasive cutoff?
So the one with the 14-inch grinder wheel. Yeah,
Yeah,
the
that's,
thing that you go like that sparks.
It looks like a compound miter saw, but you have
Yeah, but it's an abrasive, it's like an angle grinder.
a blade on it.
Yeah.
It's one of these.
Yeah, it looks like a miter.
What's the limit of this thing?
Thickness of the metal would
Before it gets unpractical. Practical range of that is like 1/4 inch. Once you start getting into like like half inch plate, yeah, you can do it. It's much slower. 1/4 inch, yeah, you could still do it. You can still cut your 1/4 inch tubing. 1/2 inch tubing, man, that would take forever. So that's why we were doing that all with a torch. Can't do it on an iron worker. Hacksaw, you can do it. It'll take you all day probably to make one cut. But I mean, the hacksaw is actually very powerful. It would be a great hazing exercise for students. No, I mean, but it does work. It's the slow version of a reciprocating saw. So if you put a metal blade on a reciprocating saw, cordless, so what's really nice, I would say, cordless reciprocating. This is an advanced hacksaw, like one of these things. If you use a metal blade, can you do like a 1-inch shaft? Yeah, you can. With a metal blade, it'll take you like a minute if you have to, but it's kind of hard work. You have to hold it. So abrasive cutoff would be easiest. You can definitely torch it, 1 inch, easy, but you got to clean it up. So always like mainly it's iron worker, torch, abrasive cutoff, grinder, hacksaw, depending on what you got. But for the 1-inch rod, I mean, you need clean ends, like say for the axes. What's the other disadvantage of torch on a 1-inch rod? It will warp it out. I mean, so you got to grind it down definitely. Like if you try to cut thin plate with a torch, it will warp it up unless you have a water bed like on a torch table. So how would you cut? Okay, let's cut thin metal, 16th inch. Best way to do it.
hacksaw, metal cutting blade on a circular saw, angle grinder with a cutting blade, the thin stuff.
Angle grinder, cutting blade, yes, dangerous. You gotta watch it. Easy to bind up. Once again, not recommended. I would actually do a metal cutting blade on a circular saw. That actually works really well. So circular saw with metal blade, and you can like Google, YouTube, like there's probably gonna be creative ways to do many different things if you don't have the right tool, but there's better and worse things to do. But actually the circular saw with metal blade, great on thin steel. And what does a metal blade look like? There's two types. One metal blade could have the regular teeth, which is just really hardened steel, or it could be the diamond style slotted blade. Okay, so let's look at blades. How do you recognize one? That is what you would use.
I can't tell which one's
Ferrous metal blade. Works great. Doesn't really dull down. You can keep cutting.
It just shapes off with those little
Yeah.
openings.
It's not got teeth. Teeth would catch and rip it very hard. So you'd have to have small teeth on another type of blade. So this would be great. Say we're making bottom of the blade for the D3D Universal. Bottom of the blade. Bottom of the plate. The heated plate. The thin plate on the bottom, which is actually 16th inch. This. What else can you do? You can do the iron worker. Yeah, it could probably work, but it might bend the edge a little bit. Because if it's so thin, it might end up bending your piece. This doesn't bend anything. It's kind of it leaves sharp marks on the metal, but doesn't heat it up too much. It works well. So what's the limit of a thing like this?
I was just gonna ask.
8th, if you go, it starts getting a little tiring on 8th because it's pretty slow. Definitely.
Depending on the sort of torque or power your machine is using, or is there a strict like rating?
So for 8th, think about this is heat. With a thin metal, you don't build up enough heat in this blade here before you cut it. Heat buildup. So once you go above an 1/8 inch, the metal will get so hot that this blade will get so hot and you'll crush it. It won't cut anymore.
Let's stuff like this for like angle iron or like I forget what the stuff is.
How thick? 1/8 inch or quarter?
Probably like not
Yeah.
like super big stuff. But like if you're doing like TV mounting and stuff like that, the rails and everything like that.
The larger they are, you can cut more ambitious stuff up to like a quarter if you have a big one. So let's look at, so that's like a handheld, relatively small one. They have ones like this, they're huge. We have one of those. It's called, let's see what comes up for a quickie saw, they call it. These ones. So this will cut 1/4 inch steel tubing. That may not be the right blade. I would do something like, this is gas powered heavy equipment kind of stuff. Cut like these are like all purpose, like concrete, metal, like demolition blades. But there's a difference between the concrete cutting blade. These are all like diamond tipped ones and metal blade. Let's look at that. Metal.
They're expensive.
Yeah, they're pretty powerful tools.
There's a lot of work.
Like for example, someone came out here with this saw. Like I would be torching like early life track tractors. We use 4-inch tubing, 1/4 inch wall. I was used to typically doing that with a torch. They had one of these and they showed me like, wow, I couldn't believe this thing cuts like that. You can cut up like through cars and metal and whatever you got. These things do that.
Looks like a robot arm.
Yeah, put that on there. So let's look at the difference. So in a blade repo that we have, there's slitted blades like that, and you have to be able to determine which is one for metal versus concrete. Because the ones that work on concrete, like the metal ones would tend to dull on concrete quite a bit. They're not really interchangeable. So metal versus concrete diamond blade. What's the difference? How can you tell? So if you look at the ones that have plain slits in them, I believe they're the ones for metal. And how do you logic that out? Because there's ones that have the plain slits like this one, and there's ones that have more like these bumps on the side. They look similar. So which does what?
That one looks like a concrete.
How do you tell?
Well,
By the
just
way-
given how the hardness of the concrete is less than a metal, you wouldn't really need those sort of flat slots. This looks more abrasive, so something that sort of
Mm-hmm.
pulverizes the material.
Yeah, so actually those on the edge here, these are more like bumps, and they kind of like smash through the concrete. So that's how you tell. Basically, the slitted ones are typically metal, and the ones with the bumps on the side, they're actually like little, very small protrusions that basically like shatter the concrete. Okay. Yeah, and you'll have combination style things like one that might have both slits and bumps. Okay, what about this one? What does this style do? And we have one of these if you look at it. This one is for a very aggressive grinding of concrete. Like say you do a foundation, you got like big bumps, this cuts right through them. So this is an aggressive concrete cutting where you're flattening out. Say you got an uneven foundation, you actually take out high spots very quickly, like uneven sidewalk, like tripping hazard. Yeah, just cut that right down with these type of blades.
Is that flat, like on the ground?
Yeah, so you do it like flat, like a grinder. You would grind flat. Like they'll be way more aggressive than you need to get out bumps like this. They'll be more like, for this, you'd need more like a buffer, which is, so what's a buffer blade look like? Because we do use buffer blades, diamond polishing blades. There's a difference between, this is not a polishing blade, this is an aggressive grinding blade. So diamond polishing blade looks different. And they're actually called pads. But what they have is a plastic material. This is what you do for like polished concrete, which is really smooth. They're plastic matrix with little diamonds, diamond powder in it. So for example, if we wanted to take this little inaccuracy or like smooth that down, you could do it with these kinds of blades. Just saying.
Do you think that would be helpful, like the CD Go Home Foundation, to get it flat?
These are, no, we lost it. Like the places where it's really flat right now, the smooth shiny parts, if you take these, it will make it shine completely, yeah. But the parts where it's like we got those joints where it's like a little uneven by like visible amount, no, you'll wear these out too fast.
So what was the solution to get the foundation?
Well, the solution for there would be a two-step process. You'd be able to do this one to take out the unevenness, and then you'd have to go back to polishing. This would get you the roughness out. Next one will be
Are you worried
polishing.
that I go grind too much in a single spot?
Yes, this is not amateur work. You'd have to have skill because you're freehand. If you're freehand, unless you have a machine that like kind of self levels, but by hand this would be very hard. So that's why polished concrete is pretty expensive. But they still have.
Not the time to sneeze.
Yeah. Okay. Back to some more cuts. Like critical thing about the abrasive cutoff is that you got to hold the workpiece down. You can do things like you notice like how did I cut the bolts with a slit down them? How did I do that?
That's what I wanted to ask.
Yeah. How did I do that? You got to hold it. You can't do any cutting without holding things down. Like if you were to try to hold it, I mean, you got to hold it somehow. Freehand, don't do that with a slitting blade. Once again, the deeper the cut is, the easier it is for your blade to bind. And you have to, a lot of times with a grinder, you have to pay attention. Like if you're grinding in say like you're inside the tube or something, or inside the larger tube with a large blade, be careful about binding, or like where one side kind of catches and the other side catches. Dangerous stuff, because the grinders there we have are 5, 9, or 15 amps. The 15 amp has got a lot of force. The 5 amp one, if you completely bind up, it'll shake you around. The 15 amp is can throw you around. So dangerous. It's a fast spinning blade. The abrasive works by spinning really fast. That's how all the sparks fly. So those things are like 10,000 RPM for the small ones. For the large grinders, maybe they're like 5,000 RPM. Typically faster than a regular cutoff saw, which is like 3,600 RPM. How do you get 3,600? It's 60 hertz. It's by the type of motor. The typical number there is 60 hertz, which means 60 per second. which means 3,600 per minute. So a typical, if you think about the numbers there, 3,600 is pretty fast. That's what you cut wood with. Slower than that, and you have things like the cold cut metal saw, which looks like a regular blade. It's got real teeth, but it moves very slowly, so each tooth only takes out so much, and the teeth are pretty small. Cold cut, just so you recognize a cold cut saw blade. They're like this. They're pretty small teeth. The blade itself is relatively thick, and you have to put a lot of force on it. Slow moving, like maybe like 100 RPM or something. It's just slow. It goes like that. That fast you can see it move. Okay, what else to cover about tools? Hollow. Okay, bandsaw. What can you do on a bandsaw? What's the limit of a bandsaw? It's good for solids, but for narrow wall stuff, the principle is you gotta have a few teeth on the metal at all times, otherwise the teeth will just rip right out. So if you do a thin tube, like say 1/4-inch tube, you want to have several teeth, so the teeth have to be very fine, like a hacksaw, for that blade to work effectively. The big bandsaw we have, some have teeth that are, you know, like a 1/4-inch apart. That would rip the teeth right out, because you want to have multiple teeth riding on the metal that you're cutting at all times. That's why solids are okay, because then you're gonna ride a lot of teeth on a solid, whereas a hollow, thin-walled thing like, say, electromechanical tubing, like conduit tubing, will rip the teeth right out of a bandsaw. So no thin stuff on a bandsaw. Annular cutter versus drill press. So we talked about, we got annular cutters. So that's the difference. What's a regular drill bit versus annular cutter? So that's the mag drills. Annular cutters, those are those annular cutter bits. They have a hollow inside. They also have a pin that's a centering pin, so when you start one of these holes, you have to start against metal. You cannot drill a hole that's been already drilled partly. Like if you're trying to drill upon a 1/4-inch hole with this, say, 1-inch blade, 1-inch annular cutter, there's a pin that's inside there that has to touch the metal so it doesn't shift around when it starts. So you cannot use this to enlarge an existing hole. New holes only, you have to do that against metal. Compared to, would you drill with this for a 1-inch hole? Like say you had the mag drill, 1-inch hole, what's advantage, disadvantage? Use this versus a solid regular drill bit. What's advantage and disadvantage of this?
Less to cut, right?
Less to cut, because it's an annular cutter. It's just got that circular area. It's faster, way faster.
Like a hole saw for metal.
Yeah, it's a hole saw for metal, except it can drill much more heavy metal than a hole saw for metal. But yes, they mentioned hole saws, but yes, hole saws can be used for metal.
I think you told me yesterday, you need to have metal in the center for that to cut.
Yep.
So the con is you can't use it to enlarge already existing holes.
Yep.
Somebody yesterday you were telling me I needed to use the angular cutter to enlarge the hole that I was trying to.
No, maybe miscommunication. You'd have to start a new hole. Yeah. Definitely. The big drill, the regular drill bit to enlarge.
Okay, yeah, because I was enlarging the hole. I had a regular drill bit on there, and you're telling me you can't do that. You have to use the angular cutter. And
Oh, because I didn't know you started. I thought you were starting with that bit as opposed to enlarging an existing hole. Yeah, because if you were starting that hole,
An angular cutter was fine.
yes. And I missed that you already had holes in there.
I was very confused. I was
Okay.
like, I'm pretty sure I can enlarge this hole with this bit.
Yeah.
Alright, yeah, miscommunication.
Okay.
What if you put another piece of metal underneath the hole you wanted to enlarge? Would that work? Then the center thing could go down to the
Maybe if it was the metal was thin enough, if that pin in the middle, the pin only sticks out so much, so you would have to reach it. Yeah. When you remount a hole from smaller size to larger size, what's the practical limit where you can drill holes with a good drill bit by hand versus you want to put it on some kind of a press, whether a drill press or a mag drill? And what's the limit of a really heavy drilling device? So, question one. What can you do comfortably by hand in terms of a drill bit? Because not annular cutters. Annular cutters have high torque, that's why those motors are slow and geared down. For safety, the other thing I forgot to mention, no gloves when doing that, because they'll bind up and rip your fingers off pretty easily because it's a high torque machine. The annular cutter is more dangerous tool that we're using most dangerous tool that we're using right now, perhaps, outside the grinders. The cordless drills don't really have enough torque to do too much damage, but I mean they still can. But I mean you still don't want to be wearing heavy gloves, perhaps if you're doing high, like big bits. Okay, but the question is, what's really easy and safe to do by hand versus it's like, oh man, it's just too hard? And what? Yeah. And also the second question is going to be why, but what's the limit by hand?
So most of the stuff we're putting bolts in, I'd say it can be done by hand. Or metal up to maybe a quarter inch.
Yeah, I'd say that. My experience on a quarter inch with a new bit, you can drill right through that with the cordless drill. The cordless. Bigger than 1/4, don't try it too hard. So what happens if you do try it and you don't have enough? First of all, it takes a lot of strength. You have to press down hard, but you can do it with a quarter inch by putting it on a table and leaning into it with your body. That's quite easy. What if you don't have enough strength? And that's why a drill press is used. It's a press because it's actually got a lever that multiplies your force going down. So what happens if you don't press hard enough and you're trying to drill a hole?
Battery will probably run down pretty good. You know, generate a lot of heat.
Heat. So what does heat do to metal?
It's a salt.
Depends how much
Makes
you-
it can make things soft and can make things hard depending on the composition of the of the metal. So on the drill bit side, do you want heat on a drill bit?
Melt.
No, it'll get soft. It will weaker. Like with heat, you get weaker. After you cool, you get harder. So, one, you're going to dull your bit. But what also happens to that metal, and I don't know if you've noticed this. Did you ever notice that you cut so slow that now the metal got so hard and you can't even drill with a good bit? That was metal hardening. So if you don't have enough force down, if you're not cutting that hole and you don't see the nice slivers of metal coming out, because they release heat too. They're hot and they fly off. If you keep drilling in there, it's like starting a fire with your rubbing sticks. That's what's happening there. So if you don't go through the hole fast enough, you're going to destroy the bit, make the metal harder, possibly make that hole undrillable because it gets heat hardened. I've seen it happen on abrasive cutoff where if you get too thick metal, like 1/2 inch or even 1/4 against a flat surface. So the technique for even 1/4, even 1/8 on abrasive cutoff, always use a corner to start on. Don't use the flat side because then the blade has got all that surface to go against. So it doesn't even see that it's 1/8 thick. It for all it matters, it's seeing that it's got a solid surface. It could be 1 inch thick because the blade is very shallow. So you always want to cut on an edge. So if you've got a tube, don't start trying to cut it like on a flat. Maybe do it like that. So you're cutting the edge. Just be careful. Like when you're cutting down, don't end up where the blade ends up perfectly flat on a flat surface, because the cut area is really large. and it doesn't have enough strength to do it. What will happen then is you'll just heat harden it, and you'll find that you can't even cut through with a blade anymore. It'll actually wear out the blade before it starts cutting.
That's what,
Did you guys have that happen?
No.
It can.
that's why I went to the macro yesterday when I was trying to cut those holes out with the handle.
So you couldn't get it through, and you probably hardened it. Yeah.
No, I stopped before that. I just noticed it wasn't cutting.
Yeah.
It's like I'm making an indentation in this, but this isn't getting. I'm not really making progress. It makes sense to go into the macro.
Yeah. So you definitely have to consider whatever you're doing. You have to think about it. Okay, if you see that the abrasive cutoff is not cutting, and it should be, like, stop a little bit. Maybe, okay, is the motor weak? Am I actually hardening the steel because I'm cutting against a flat surface? Because good cutting should be good sparks on abrasive tools, and on bits you should have clear shavings, not those ones that turn like purple and hot looking, or even potentially like glowing. That's not good. You gotta, part of the heat dissipation is that you got the shards coming off, releasing some of the heat. And water lubrication, like diesel, is great for, or even water, just for the annular cutters. Make sure that when you're going down, you're not going too fast, but fast enough that you get good cuttings. So that applies to both drill and, you have to get a feeling for this, where on an abrasive cutoff, you can't press down too hard, you'll burn out the motor. You can't press too light, you'll go too slow, and you'll, instead of cutting, you'll be warming it up, and you'll harden it. So, like good, you have to kind of think about what, get an understanding for what a good cutting rate is. That you kind of maybe like watch some YouTube videos, or just get experience. Like, what do you see is like, okay, that was a clean, good, fast cut. Knowing that, like 1/4 inch, yes, you should be cutting readily with the abrasive cutoff. Yeah, and with drill bits, clean shavings. If you get very tiny little things, I mean, something's dull, you're kind of like rubbing against them, making tiny particles come up. Because the way a drill bit works, it's supposed to cut long slivers of the metal. Yeah. Okay, what else? Question?
So how did you?
How did I cut that?
Yeah.
So if you notice, that was a threaded bolt. So when you try to cut a threaded thing, note that you can put nuts on it. So what I did is took a piece of metal that had a hole in it, and I put a nut on the top and bottom, so I could hold that. It was a tube. I held the tube. I actually clamped the tube, and then the bolt was sticking up. It was through one of the hole tubes, or a plate. That was I could put the bolt in vertically, put a nut on it, and now it was firmly held, so that I could cut down straight with the abrasive cutoff. I just put it in the vise of the abrasive cutoff, so the metal I held in the vise of it. So yeah, that's the key to holding it. Couldn't do that by hand. You can't hold it by hand because there's a lot of force on the cut. You do have to cut because it's. Say again?
Just need a good pair of pliers.
Yeah, strong pair of pliers. That was a 3/4 inch bolt, so that's like a lot. That's a lot. Slow cut. So at that point, I had to watch out for. Okay, I need to press down hard enough so I'm not heating it, but instead really cutting. I had to pay attention to that, and otherwise have the hold very firm in the vise of the machine.
Means you had to have some like extensions because the vise is.
Yeah, I took a 1/2x4 strip of the whole metal with the holes. I put that and clamped it down with a vise, and then the bolt was right there accessible. Yeah. What else? For torch, I mean, torch is good multi-purpose cutting. You can cut anything. Like I cut the 3-inch shaft with that. That was like the only tool you could do with that. You can put it. Well, no, bandsaw. Bandsaw would be the cleanest, but it would take more time than torching. Torching was okay, but it really messy cut. You gotta grind it down at the end quite a bit, all kinds of slag, and you kind of got to rotate it as well. A lot of slag with acetylene torch. If you go to hydrogen, which is that's something we gotta start using here, but hydrogen torches don't have the slag problem nearly as much. Very clean cuts, and they could also do aluminum and other metals like stainless steel or copper. I think they cut through copper too. Acetylene torch doesn't cut well through, like you can't cut aluminum with it, or copper, because
Aluminum? With what?
no, it ends up melting, and it just does like this pretty much a molten channel instead of a cut. Yeah, because I think the aluminum for some, I don't know, it sounds, I don't know why. Why
Doesn't
can't, why
oxidize
not?
in the same way?
Yeah, it doesn't have a burn as fast. Why not aluminum
Research
with
are just
acetylene?
What?
That's the important question.
Asking the important question.
Why would it fail? Why?
Because aluminum, oxyacetylene will get aluminum hot enough to melt away, but no way for a neat manner. It just melts. It tends to melt it more than cut it. It just doesn't work for some reason. While the oxyhydrogen works better. What else on cutting? Reciprocating saw. On the reciprocating saws, there's two types of blades. Wood blades with larger teeth. The metal blades, you can recognize they're very small teeth, and they'll say something like metal blade on it. So yes, you can actually cut metal with a reciprocating saw, but make sure you would have the right blade on it, like cutting nails and stuff like that. Yes, we do have the.
What about, like, is there an approach to this where, like, I guess like a more physics oriented, or like, is there some field that's like the intersection of, like, there's like material science, right? You talk about like cutting metal and wood, but I would be interested in like knowing how I can, or like a more generic approach to cutting any material.
Clamp it down. Don't get your fingers in the way.
You have to consider it's about the strength, melting temperature, oxidizability. Primarily, like the materials properties you're talking about for metallics, it's like metallic versus stone or wood. Wood has fibers.
Well, we're going to do like plastics, right? If we're 3D printing polyethylene and all sorts of things.
Yeah, it's like industrial engineering. So that was the undergrad at a double major in industrial engineering. These are classes in all types of manufacturing stuff, material science and everything like that. I didn't pay much attention at the time because I didn't think I was going to use that stuff later in life. But we took courses and we had whole classes on the science of manufacturing and what processes to use, what materials.
Yeah. The idea, biggest points are for if you've got thin material, thin teeth, small teeth. Thick material, you can get larger teeth with flame. It doesn't matter. Like for irregular shapes, for cutting precise geometries, that's CNC. Obviously, by hand you can only do so much in terms of how straight you can hold things. You can use templates. If you can lay something against the template, you can get down to like probably like maybe up to 16th inch accuracy, because the accuracy is that of template plus how straight you're holding the thing. Like if you hold it straight down for a torch versus you got it at a small angle. There's circle cutting jigs for torches. So if you want to cut like a big hole, there's a thing. It's like a protractor thing where you lay the torch on a pivot and you kind of just move it in a circle. So for a large hole, because the question comes up a lot of times, okay, holes. So yeah, holes are common features and different things. For that, ideally, you got CNC torch. If we're making the plates right now for the carriages, the ideal tool would be a CNC torch, because we've got some elongated holes for adjustments. How you do elongated holes, that's hard. That's only like mill territory. You'd have to mill it. Or what we did right now was we drilled 2 holes next to each other, torch out in between for a slotted hole.
Or we
Um,
just kept drilling in between them until the 2 holes met.
Yeah.
Doing yesterday.
Did it work?
Yeah. I mean, it's
Kind of works except for like the edges where it gets, the edge might be a little, come in a little more or something. What else? There's on a lathe, meaning a thing that spins something, like if you have your drill or a cordless drill, you can hold a rod, and if you hold some kind of a grinder or cutting tool against it, you can cut things that way too. They have like cut off blades, like on a lathe, a thin knife-like structure that you poke it into the material and it cuts it, it shaves it off. For grinders, the difference between another wheel, there's buffing wheels and there's grinding wheels. Buffing wheels are the ones that kind of have like the flaps or the pads on them, which are used for polishing things, not so much grinding. Buffing wheel grinder.
So would a lathe be the type of, the lathe with the type of blade that you're describing, is that likely what's used for making things like our drill bits?
Yeah. Drill bits, yeah. So how do you do that? Let's talk about that for a sec. So buffing. These kinds of things, that's a buffing wheel. It's pretty much got sandpaper-like material. Don't use that to grind stuff, you'll just wear that right out. But this is good, like say you want to get rust off or to polish, shine something up a little. So we have some of these. Don't confuse them with regular grinder wheels. Grinder wheels, use the fat ones. Try not to use the cut-off grinder wheels, as I mentioned, for safety reasons. I mean, it's the safest if you've got like really thin material. Yeah, you can cut off with a cutting wheel. I don't like it in general because I just put on a cutoff saw, the abrasive cutoff. So on a lathe, so the CNC lathe concept, that's how you'd get okay, so how do you get super precise? So there's milling and there's grinding. So where do you do, or what are the limits of high force machining, which is drilling, milling, lathing, versus grinding? How do you actually get the most precise features? And the answer is grinding, actually. So a drill bit would not be made by machining it. You might start it, but for the precision you want a grinder. Why? So why a grinder? So if you want a grinder,
Surface characteristics?
force, amount of force. So what do we say about grinder wheels? About their speed.
High speed.
High speed.
High
If you're
RPM.
high RPM means you need less force to do an action. With the machine cutting tools, they're hard contact, one thing against another. Think about how much force it takes you to drill a hole in metal. A lot of force, contact machining. So if you want the super precision, you're going to end up with grinding. So say you want to do a drill bit, you might preform it to like a shape, maybe like with the flutes in there, even by like twisting a piece of metal. But how do you get that sharp edge? That would be grinding there. And why is that? Because the drill bit at the end of the day wants to be made of hardened material or hardenable material. So first of all, the machining would not work well because you're working on hard material. And then for precise features that are very sharp, you want the least force possible, because once you go against something, especially if it's like a long tube, that's your drill bit, you know, you have to support it very hard in order to machine it heavily. But how do you do like a very tiny drill bit? Well, you can't, you'd break it. So the only way you could do that kind of stuff is grinders. So the limit of grinders is air bearings. So smooth that just the friction between two surfaces serves enough to trap air in there for a completely smooth glide. So there is an open source air bearing lathe. Look at this. This is it. So what you do for super high precision, if you want to get engines and like cylinders and oilless engines, rocket engines, this is what you get up to, and that looks like a lathe there, but and that is, but
The lathe DIY?
part. Let's see, this guy actually built this thing, but yeah. So actually, this is Dan Gelbart. He does this crazy high-tech machining stuff. But what do you do for an air-bearing lathe? You have a grinder as the active tool, so you can be using that lathe, but the thing working on it is not the tool bit, but a grinder. So that's the territory of CNC grinding, which gets you such precision that when you make, I think he shows it at the end, the grinder part is that tube there, that thing. Yeah, watch this video later, but he shows the product of it. No, what am I saying here? It's not in this video.
That's a grinding wheel doing the thickness. That's a big, so that's like a... So you wouldn't want the circumference of the disc to diminish too quickly, because then your CNC is off, right? Like using abrasive discs, they will eventually wear down.
They wear down, and that's the other challenge with those. You gotta even them out or use new ones after some time, because they will wear down. So you can.
Yeah.
But here, in this video, take a look at that. It's quite instructive. 2 cylinders, so you make 1 cylinder and a pin that goes inside of it. And because of the precision, no oil, no nothing, he spun that and the thing free spins forever. That's called air bearings. And that's what's used in super high, fast rotating things like jet engines. You can't have ball bearings in things like jet engines. It's just air gliding against air. And that's how you do oilless engines. That's like the next level of beyond internal combustion engines of today. Ain't happening. Industry's not going to do that. That's disrupts an entire civilization. So,
I think it's
we should do this.
like, even with alternative fuels, like it's almost impossible to get away from lubricants and all types of other things that are fossil fuels. So you need some other technology for things like that.
It's not why we're not switching from oil.
No, it's definitely not why, but it's just like, even if I was like, oh yeah, I'm gonna retrofit all of my two-stroke gasoline engine appliances to run on hydrogen, it's like, that's cool, but I still gotta put oil in it.
Right.
You know?
Exactly. So the hydrogen economy comes at the cost of access to this technology, but it's doable. It's called grinders and lathes. And how do you get the super precision surfaces to move on, right? We've done our torch table, not that precision. How do you get down to like 1 micron flatness? And that's actually very common already in tile, that industry. So the most advanced, this example here, how do you get the super precision motion? It's on a granite, granite slab. It's super precise, super flat.
Really? Slice on granite.
Yep. So,
They just keep like a molecule layer or atom, whatever it is.
well, so people make marble walls and granite, like marble. That technology they use to polish is super, super smooth. It's lapping. But that technology has been around for a long time because you have smooth marble for a long time. But those things are like super precise. So the way to make one of these air bearing lathes is you get a granite for CNC. You get these blocks of granite This is what you do. You want to make air bearings, you start with this. Go to Amazon, get a $200 block of surface plate. It's going to have different grades. I don't know what they mean. I haven't looked into this too much, but these are going to be super precision pieces of rock.
What's the most expensive one? What's the 1,200-pound one? It's on the plot. Yeah. $1,000.
48 inch by 36 by 6 inch, so it's still tiny, but it's quite long. Oh no, that's big. Wow, that's a big chunk. 48 by 36 by 6 inch thick. Oh yeah, that's gonna be like a ton of weight or something. But it's not that expensive to get like capacity to make jet engines for $1,000. It's not too bad.
What kind of bit do you use in granite?
Hmm.
What kind of drill do you use for granite?
It's not drill. It's oh yeah. Well, you got to do like basically like diamond cutting. So we didn't talk about.
The foundation.
Yeah, we could. It would be quite expensive.
We just grab one of those and then
Tile saw. This is like tile saws. Well, so once again, you use the. That's not precision cutting, but how do you do this? How is granite smooth? How is granite cut? It's lapping. It's like, no, it's different technology, but it is where it's like it's called lapping. If you take two surfaces, keep rubbing them against each other, they actually end up wearing out to perfect smoothness. So there's a whole technology, but that's well established, and you can get these. I mean, that block of granite, it's not like $10,000. They're huge. I mean, that's like a 4x. It's like a 4x4 by 6 inch. Freight is going to be quite a bit on that, probably.
It's like shipping out of northern India or something.
We're not going to buy that right now.
£1,000 free delivery.
No, it wouldn't be free delivery, but it's actually not bad. Like 6 by 8 inch by 2 inch for that super level of precision down to like a micron, which is 1/10 of like one, or a micron is 25 microns are 1/1000th of an inch. So down to 1 micron is like 1/25th of 1,000th of an inch. But that's readily available. That's the good news. So you can do this. Stock.
CNC cutting.
They use it for applications like machines that require super precision, like whatever in space tech, maybe semiconductor tech, precision machining. Yeah. Like if you're going to be making like CDs, you're probably operating on a table made of this precision granite, things like that.
So 1 micron?
Yeah, 1 micron flatness. 1 micron, no problem. They probably make.
Let's get these for the D3D base.
Mm,
Spend.
I like
Oh God, we have
this,
lots
yes.
of money to have
Mhm.
space.
Yeah. Okay. Some of the last things. Cutting through very, very thick steel with very good precision. Not hot wire. It's called
DCM.
EDM. EDM is right there. Didn't cover water jet cutters, but they're very effective. Just shooting a very high force jet of water to pretty decent precision. There's things like hot wire cutters for styrofoam, like if you're making styrofoam for like insulation or whatever. Thermite, I'll point out that one. That's like, what if you want to cut, you're an underground rebel wanting to derail a train, you use thermite. But that thermite is, it's a mixture of aluminum and something else, I forget what, but it's this crazy thing. You gotta Google thermite, but
Then Neil told about that, like rust, pieces of rust and metal
Yeah.
is used.
it's like rust and aluminum and something else. It's very common materials, but you mix them together and they release so much energy it'll melt through anything. So if you put a little pot of that on a metal beam, it'll just melt it in a second. Like, it's crazy stuff.
How do you trigger that?
shoot it with a shotgun from a distance.
I think it's just by mixing those together, and that's it. And they just start heating up in a few seconds and they just go like
You can just see on
thermite. I mean,
people just putting thermite all over cars.
Oh yeah, microwave stuff.
Bam,
That.
and just the car starts and it's wild.
American baby. that where I come from.
Thermite.
You go to
This
rural
guy.
Pennsylvania, and it's-
Oh, that's how they. Oh, okay. So this is constructive thermite. That's how they would melt the tracks together.
Yeah. I've seen
Um,
soldering, like military soldering kits work like that too.
Yeah, yeah, things like that. Anyway, but for cutting regular purposes, pay attention to like tool speed, like profile of what you're cutting, thin stuff versus thick stuff. If you want to cut, like if you're cutting metal, that's like abrasive cutoff is your, if it's a round thing, solid or hollow. The abrasive cutoff does not worry about thickness of the wall of the material. Like thin tubes are easy to cut. So I mean, I think the abrasive cutoff is the most universal, because if you had a higher performance thing like the cold cut metal saw, or even like the metal blade on a circular saw, the tricky part is the clamp down part. Like the abrasive metal cutoff is very useful because you've got the clamp down. It's not something you gotta like clamp down some other way. So it's generally it's really good for metal cutting. That plus the iron worker plus the torch gets you just about anything you want. Then you've got the option to do a lot of things using reciprocating blades and circular blades on regular saws. So anything from rock to metal. Not only wood, because you only think like those circular saws are for wood, but they're not. You can cut other things depending on what blade you have.
So it's like,
That's about it.
go from the iron worker, well, I just think about that, the iron worker being not as accessible, right? And so like in the,
It's a heavy machine, yeah.
yeah, so for like the, you know, the global village construction set and how we work, something to keep in mind as we design is what level of precision do we need and how do we design everything in a way so that with simple tools, everybody can do it.
Yeah, and what are those three tools? It's a welder, a torch, and a grinder. And with that you could build a tractor, you could build a torch table, you can build our printer, almost. But basic workshop like MIG welder, acetylene torch. I actually put mag drill because that's quite useful wherever the acetylene torch won't do. But I mean, you can do anything that a mag drill can do on acetylene torch. It just won't be as clean. But if you were stuck on a desert island, you had a choice of three tools. It would be a welder, a torch, and a grinder. If you're reconstructing modern civilization, because that involves metal. Those are the three kind of tools.
And why a macro versus just very good deal for us, just for portability?
Mag drill allows you to do big holes in places where you can't even access a drill. Say you had to drill a hole on your tractor frame. You can't put it, like, you really need a really strong vise to hold the drill. You can't get your drill press on it. You can't hold it by hand. Mag drill allows you to do that very easily, actually, like upside down or whatever, right on the side of something. That's why I put that in there, because that is very useful. But if you have a torch, you can probably still get that hole in there. Yeah. That's basic workshop, and then that's a useful page. Yep. Anything else? I think that's it.
I thought that was a good discussion.
Yeah. Yeah.